I'm Mrs. Calvin, and this is AP Chemistry Notes on Accuracy and Precision. So in chemistry, numbers mean something a little bit differently than sometimes portrayed in math classes. So numbers that we communicate in chemistry can either be exact or inexact. An exact number is something that is counted or defined. Mostly conversion factors that we're going to be using will be exact numbers. So for instance, 1 dozen is the same thing as 12 of an object. So that is an exact number. 1 inch equals 2.54 centimeters. Inexact numbers are going to be numbers that we measure, and how confident we are in that measurement is going to be communicated by the number of digits that we share. So 12 is going to be different than 12.0, which would be different than 12.00. So these are communicating different amounts of precision. So the reason why we have to communicate this is because lab equipment and humans, of course, have error, and this is going to bring uncertainty into our measurements. So when we are measuring something, so for instance, in this thermometer here, you can see the reading is here somewhere between 25 and 30. And so we are definitely sure it's more than 25 and less than 30, but where exactly between those, we're not sure about. And so that second digit, we're sure about the 20s, but that second digit, the ones place, is uncertain. And so it's considered reliable, but not exact. So we've had to guess it. So, we have a difference between accuracy and precision. So precision is going to be related to our lab equipment, how precise something can be. We can also look at our data as being precise. So if I have a series of data that I've taken, measurements, for instance, how close they are to each other, that is going to communicate the precision. To calculate the precision, we will use standard deviation. So that's how much each data point that we have, or each measurement, is how far it is from the average. And so if data points are pretty far from the average, then we don't have very good precision. And we are going to communicate precision by using that plus minus. So plus or minus X amount. So for instance, plus or minus 0.01 is going to be more precise than plus or minus 1 gram or milliliter. And so the precision here we can see in these devices. So if I was going to measure a certain amount of liquid, the graduated cylinder is going to be more precise than this beaker would be. And that's because of the number of lines that are here. And so I can say with more surety how much liquid I am actually delivering. The other part is going to be accuracy. So accuracy is how close a measurement is to the true value, and so the accepted value. And so to communicate this, to calculate this, we're going to use percent error. And so it's the experimental value that you measure versus the accepted value that we should have gotten. So we always like to use these dartboards as examples of accuracy and precision. So precision, the first one is showing good accuracy because it's on the bullseye, and good precision because all three of these darts are in the same location. The second one is not accurate because it's not on the bullseye, but it is precise because they're all grouped together. And then this last one is not accurate or precise. So to communicate precision, we are going to use something called significant figures. So all measured digits, so for significant figures, all the measured digits plus the one uncertain one, includes the one uncertain one, is going to be considered significant. So to count up how many significant figures there are in a number, there are rules that we need to learn, memorize. So the rules are all non-zero numbers count. So 1 through 9 are going to be significant. That's an easy one. It's going to be the zeros that are going to be difficult. So zeros that are in the middle of non-zero numbers, these count. So for instance, the number 101, the 0 is in between the two ones, and so it counts. And so 101 has 3 significant digits, the 1, the other 1, and the 0 in the middle. Zeros to the left of numbers never count. So I could say 0, 0, 0, 1, 0, 1. And so it's still 101. The zeros in front don't really mean anything. Zeros to the right are complicated. Sometimes they count and sometimes they don't. And what's going to determine if they count or not is whether or not a decimal is present. Now, I don't care where that decimal is. It doesn't matter where it is. What matters is if it's there or not. So if a decimal is present, then those zeros to the right do count. If there is no decimal present, then it doesn't count. And again, remember, we care about this. Okay, chemists care about this because it's going to communicate how sure we are on these measurements. All right, so let's take a number. So this is 20,394,000,000. So how many significant digits are in this number? So the 2, the 3, the 9, and the 4, those all count. So that's 4 significant digits. I have a 0 in the middle. That 0 in the middle counts. The zeros to the right, there is no decimal present. So those zeros do not count. So I have 1, 2, 3, 4, 5 significant figures or digits. Okay, but what if this was something that we actually measured? And I know that when I measured this last 0 was that uncertain digit that I measured. So I remember it's reliable, but not exact, but we can count it. So how do I show that this number, this 0 matters, but the other ones don't? So the answer to this is scientific notation, and this is why we use scientific notation. So in scientific notation, the front part of the notation, this part, all of these digits count. So I have 1, 2, 3, 4, 5, plus that other 0. So 6 significant digits in this number. And then the times 10 to the 5th tells me how many of the zeros didn't count. So these 5 at the end did not count. And so they can just kind of be placed in there and we don't care about them. They still are important because we need to know that this is 20 billion and not just 2. All right. So the last thing is using these significant figures in calculations. So let's say you measure an amount of liquid 3 times, and so you need to take the average. Well, you're going to be adding those together, and then you're going to be dividing. So we're going to have different rules for adding and subtracting and multiplication and division. So when we're adding or subtracting, your answer can't be more sure than your measurement. I can't measure something that's 12.0 centimeters and say, and another one that's 1.0 centimeters and say it's 13.0000. Again, I'm communicating to you more precision than I actually measured. So answers need to be rounded to the least significant decimal place. So in this example here, they're talking about a population of a town. So I have 30,000 people. I have 35 births and then 13 people that migrated out. So altogether, I have 30,022. Now, do I really have 30,022 or did we guess at 30,000? Maybe there's actually 30,150. So because this is not a very sure, very precise number, our answer has to be rounded to whatever the last significant number was. So in this one, they're showing the blue is significant. So this is a ones place, this is a ones place, but we are only significant to the thousands place. So my answer can only be significant to the thousands place. So it's 30,000, but again, this 0 and this 0, how do we show that the blue one is significant and the red ones are not? You put it into scientific notation. So it's 3.0 times 10 to the 4th. All right. So what about multiplication and division? I think it's actually a little easier. So with this one, your answer is going to be rounded to the same number of digits as the measurement with the fewest sig figs. So in this one, I'm dividing 351.2 miles by 5.5 hours. This one has 4 sig figs. This one has 2 sig figs. My calculator spits out this number. I have to round it. What do I round it to? Well, it can only have 2 sig figs because that was the least significant, or the measurement with the least significant number of figures. So it's going to be 63.8. I need to round it up to 64. Okay, and that's it.